Okay, this problem is one of the examples where we're gonna need an iterative process to come to our answer. So let's go ahead and just dive right in. We have this system here. They give us several loss coefficients of this looped type of system. And from here, we're going to go ahead and let's write out the Bernoullis. So P1, elevation, velocity. Oops, let me get this going. Okay, velocity plus the pump portion, and then P2, specific weight, Z2. Let me clean this up, the Z's a little bit. Okay, velocity, and then head loss. And the head loss here is the summation of all of these. So we have that the head loss is the viscous through the whole length of the whole thing, and the sum of all of our elements, and then V squared over 2G. Now it's going to be the same velocity throughout, and when we go through this analysis, we're going to go ahead and assume that both points, 1 and 2, are here. It just made a loop. And if it makes that loop, we can say that the pressures are 0, the velocities are 0, that the elevations are equal. So really, and it makes sense if you think about it, that the pump effort needs to be equivalent to the losses of the system. So that's really what we're doing here. And any of these circular systems, you're going to have a similar type of balance, is that you need to have a pump that is sized appropriately for all the components of the system. And that's a sort of using Bernoulli's to sort of get to that conclusion. All right, so from here, first we need to figure out the pump. We're given the pump information. We're given that is 200 foot-pounds. Now we know that the power, relating the power to the pump head, we will have volumetric flow rate and then specific weight. So we have this. We're going to go ahead and plug in 200 foot-pounds per second in the numerator. In the denominator, we'll have 62.4 pounds per cubic foot. And then for our volumetric flow rate, like, we do not know the flow rate of the system. But one of the things that we're going to try to find is velocity. So you could go through the system trying to find flow rate. I'm going to go about another way and trying to find velocity. And the reason is that we're going to have Reynolds number as a function of velocity that we need to put in. So I think it's a little bit more straightforward to use it for find velocity. So I'm going to make that substitution for pi over 4. And now we're fortunate in that the diameter of the pipe in our system is consistent everywhere, of 0.1 feet. So we will have 0.1 feet squared, so that is our velocity. Our area, and that's going to be multiplied by velocity. So in that square bracket term is our flow rate. So we will get that our pump head in terms of velocity is 408 divided by V. Now let's go back to our head loss. So we know that that's going to be equal to our head loss, which is going to be our friction factor, which we don't know. So friction factor times, you know what, let me put a bracket here. Friction factor times 200 feet, because it's equivalent of 200 feet of length, divided by our 0.1 feet. And then we have all of the losses of our system. So what do we got here? This, elbow, but there's not just one elbow, there's 5 elbows, and then filter, if I got all those right. So 1, 2, 3, 4, and then 5 of those. So we have 0.8 plus 6 plus 12 plus 1 plus 5 of 1.5. All right, we got all that. Velocity, didn't do that. Velocity squared divided by 2 times 32.2 feet per second squared. All right, now we got everything. If you take this whole expression, this on the left-hand side and this on the right-hand side, if you calculate that and simplify and solve for velocity cubed, you will get 13.13 over friction factor plus 0.01365. Now, I'm going to hold on to this expression. So I'm going to say 1, hold on to it. So now that we have that, we need to find friction factor. And how do we do that? We can use Reynolds number. Reynolds number is, so we'll do rho v d over mu. So in this case, 1.94 slugs per cubic feet times velocity times diameter divided by viscosity, 2.34 times 10 to the negative 5th pounds second per foot. We have that. Or we get Reynolds number to be 8,290 times V. Let's hold that and hold on to that. So we have some expressions here. So this is where we have some options. And one of the options, so I'll just say option 1. Option 1 is to guess a friction factor. Like we don't know what it is, but we just have to guess. And then when you plug in the friction factor, you plug it into 1, you'll get a velocity. You'll plug it into 2, equation 2, and then that will get you a Reynolds number. And then that, you go back and get a friction factor. And depending on what that is, if I'll say do again, if f at your end of your iteration is not equal or not close to the one that you started with. Now, if they are close, then you get your answer, you're fine, and then you can find your velocity and get your final answer. In this case, we're trying to get flow rate. You can do that. And then this is where you would use the Moody diagram to help in your analysis. That is one option. And that's fine. That's valid. You can do this. And then if this was the case, I'd probably set up, or you maybe set up an Excel sheet just to help you, because if you're going to do the same calculations over and over again, something like that will help you. However, speaking of using software, option 2. Now, those equations that estimated the Moody diagram, for example, the Colebrook equation, so 1 over, I'm going to put that here, 1 over square root of friction factor is equal to negative 2 log of surface relative roughness over 3.7 plus 2.51 over Reynolds number square root of f. And if we use that, there's my third equation, right? So 3 equations, 3 unknowns, If you, for example, plug that into equation 2, we can get an expression, and then combining all of them, ultimately we need to find, it'll be some type of root finding formula. So I would say it would combine equations 1, 2, 3, and solve for a root to find velocity, because that's ultimately what we're trying to find. So those are the two options that you have. And this is where you would need either some type of software or some type of iterative process. So it's not going to be a straightforward method of doing this. And they also gave us the relative roughness. I forgot to highlight that. Let me go ahead and put that down here, because that was going to help us in all these aspects. So those are your two options. I'll leave it up to you if you want to go through all of that yourself. So with that, so in terms of what the answer is, your velocity will be 6.29 feet per second, and that is your velocity for your system. And then when it goes back, it says determine the flow rate through, it says flow rate through the filter. So we'll have to go back and get a volumetric flow rate. It will be 6.29 feet per second, and the diameter that we used in all these cases is pi over 4, 0.1 feet squared. So Q equals AV. And then when we go through that calculation, let me go ahead and do that on my calculator real quick. We will get 0.49 cubic feet per second.